Imagine a severe typhoon hits. Rapid floodwaters submerge entire neighborhoods, power lines collapse, and ground teams are forced to move in blind.
My name is Fire Officer 3 Fulbert Navarro. I am assigned here in Cebu City Fire Station as an investigator. Our investigation is lead fire arson investigator. There are some fire patterns that could not be seen on the eye level lang nimo on the ground. There are some patterns that can be best appreciated from a higher vantage point. So which can only be provided drone na lang which can hover directly above. No?
Disaster responders rely on drones for an eye in the sky, but conventional off-the-shelf multirotors die in under 20 minutes.
Flight time sa drone is limited by its battery. So disadvantage na limited yung flight time to 35 minutes only.
The second a crew locates stranded families or plans an evacuation route, their screen goes blank.
In disaster response, short flight times isn't just a technical limitation, it's a life-threatening bottleneck.
As engineering students, we built a solution, an endurance-focused drone engineered from the ground up to stay airborne significantly longer.
Designed from the ground up, airframe components were 3D printed using PLA Aero and PETG with optimized slicer settings for strength-to-weight performance. Electronics were made entirely from scratch, from the architecture, power distribution, PCB, and battery. They were fabricated for robust, streamlined power and delivery. And the airframe assembly and avionics were integrated using a custom firmware architecture, establishing stabilization logic and bimodal transition control synchronized with real-time IMU sensor data. Thrust power and endurance tests were conducted alongside PID tuning via tethered flight, validating hover stability, climb rate, and operational flight time for disaster response deployment. The Alpha prototype is a bimodal tail-sitter UAV with VTOL and fixed-wing crews, boasting a wingspan of 1.13 meters with a weight of 1.8 kilograms. Airfoil used was the NACA 0012, which is symmetric to be stable during modes of transitions. Motors are dual T-Motor MN3508 brushless motors, mounting one per wing, with a frame, a 3D printed PLA Aero body with PETG, and carbon fiber rods for reinforcement. Flight modes include a vertical hover and takeoff, and horizontal fixed-wing cruise with the capability to hover and loiter at designated areas of interests. To validate the aerodynamics before physically building anything, we ran computational fluid dynamics simulations. We sized the wing for a stall speed of 13 meters per second under full 1.8 kilogram load, giving us a reference wing area of 0.212 square meters. CFD confirmed structural integrity up to 17 meters per second cruise. At the critical 12-degree angle of attack, the wing generates 18.4 newtons of lift. That's 1.02 Gs with a 2.71 safety factor. The airframe holds. Peak aerodynamic efficiency at 9 degrees angle of attack, the lift-to-drag ratio hits 11.35. That's the sweet spot we target in cruise. We also ran finite element analysis to make sure the 3D printed PLA Aero with fiber reinforced chassis could handle real-world impact loads. The modular fuselage design is intentional. Outer panels absorb kinetic energy and can be replaced, protecting the internal avionics bay. Landing struts are printed with PETG, attached directly to the main carbon fiber spar of the body to absorb landing forces. After a high kinetic impact test, post-flight inspection confirmed zero internal components failure. For the propulsion testing, we characterized dual motor propulsion system empirically. The system achieves a thrust-to-weight ratio of 1.42, well above the 1.3 minimum for takeoff. At hover, We run about 62% throttle with a 38 power reserve, meaning there's headroom for gusts, maneuvers, and payload. Climb rate tests show a terminal climb velocity of 3.0 to 3.5 meters per second, solid for a rescue platform. Now the big question, endurance. The custom 6S lithium-ion pack gives us a 74.6 watt-hours of usable energy. In pure hover, 37.3 minutes, already competitive. In fixed wing cruise mode at 18 meters per second, 82.24 minutes, a 3.2 times increase over hover alone. For a realistic disaster mission, combining hover assessment with cruise transit, we modeled a 57-minute hybrid mission profile. Compared to the 20 to 30-minute quadcopter ceiling, that's not an incremental improvement. That's a paradigm shift. The PID control system was tuned for transitional stability, settling times of approximately 3 seconds across all axes. That means the drone stabilizes in under 3 seconds after a disturbance, fast enough for rescue operators in turbulent conditions. An unexpected high-impact event tested the design's limits. The modular design means the frame survived test crashes where the avionics bay stayed intact every time. This isn't a simulation. This is the hardware we designed, printed, assembled, and flew. So what did we prove? Max cruise endurance is upwards of 82 minutes, where a hybrid mission profile lasted upwards of 57 minutes, where the endurance is 3.2 times longer than conventional quadcopters, with a thrust-to-weight ratio of 1.42, with a safety factor of 2.71, with 3 seconds PID settling time, with a peak lift-to-drag ratio of 11.35 at 9 degrees angle of attack. By breaking the battery endurance trade-off, we transform brief, panicked flight windows into continuous, uninterrupted aerial intelligence.
Under SDG 11, this gives local governments persistent overhead coverage to safely route emergency crews through active hazard zones without losing visibility.
And under SDG 13, it gives climate-vulnerable communities a rapid deployment tool to track rising floodwaters and assess damage in real time.
Crucially, we didn't just buy foreign parts. We designed and fabricated this high-endurance hardware locally.
Aligning with SDG 9, we are proving that student-led engineering can replace expensive, imported drones with localized, battle-ready technology designed specifically for our country's disaster landscape.
We've taken this project from academic research to an industry-ready prototype built to stay in the air longer when it matters most.